Hi everyone, let's look at today's LeetCode daily challenge. If you like my explanations, please do subscribe and like and share the video with your friends. It's going to encourage me to record more videos and improve my explanation. Thank you. Let's take a look at the problem. So we are given an array, integer array, and we should find sum of mean b, where b could range over every contiguous subarray of R. Since the answer is going to be big, we want the answer to be returned modulo 10 to the 9 plus 7. So what is the problem saying here actually? It's saying take any subarray, then take the minimum of that subarray, and then add all of them together, and then return that. So here, if we look at this example, these are the 4 subarrays of length 1. These are the 3 subarrays of length 2. These are the 2 subarrays of length 3 and 1 subarray of length 4. And these are the minimums, 3, 1, 2, and all of them. And the sum of them is 17. So one way of looking at this problem is to look at each element. We look at each element and we say, hey, 1, to how many subarrays are you going to contribute? And you are going to be the minimum. And we do that for all of them. If we do that for all of them, then we have counted all of the subarrays, basically. Because each subarray has a minimum, and we are considering all of the possible minimums. But how do we do that? Let me delete this example. I don't need it now. Let me have an imaginary number like 4. And there are some other numbers to the left of 4 and some other numbers to the right of 4. So in order for 4 to be the minimum in one subarray, first of all, 4 itself should be included. 4 itself should be included. And we can choose any index from left, like this one, this one, this one, for the left, and any of these ones from the right. Or if we want the length to be 1, we can also choose 4 itself for the right one, or use 4 itself for the left one. So the number of subarrays that include 4 is going to be the red arrows, number of red arrows times the number of green arrows. This is the number of subarrays that include 4. But that doesn't mean that in all of them, 4 is the minimum. No, 4 is not the minimum in all of them. So what should we do? We should get rid of some of these arrows to make sure that 4 is actually the minimum. So that means when we are going to the right, we should stop before a number that is smaller than 4. Does it make sense? And when we are going to the left, sorry for using so many colors, when we are going to the left, we should stop before a number that is smaller than 4. Why? Because if we find another number that is smaller than 4, then 4 is not going to contribute as the minimum of that subarray. That number is going to contribute. So we stop before that one. Stop before that. So any number here is going to be bigger than 4. For example, this is going to be 5, this is going to be 9, this is going to be 20, this is going to be 11, 12, 10, something like that. So this 4 is going to be the minimum. But what if we have another 4? What if we have this 4? Okay, I should delete this as well. What if we have another, let me add this example. So what if at some point here we have a 4, let's say, and on the left of it, on the right of it, we have a 3. Do we stop before this 4 or before this 3? The point is that if we include this 4, then there is some subarray like this one that is going to be counted twice, once by this 4 and once by this 4. So in order to fix this, we are gonna make a rule. So each subarray is only counted once. We are gonna say only the rightmost minimum is gonna consider contributing to total sum. So what does that mean? That means when we are going to the right, a stop before a number that is smaller than or equal to 4. So if we see this 4, we can go only these many numbers, like we cannot go until this 4. But for the left part, we still have the same rule. We have the same rule. A stop before a number that is smaller, like that is smaller. The same text. Stop before a number that is smaller than 4. So our problem is kind of now reduced. So if we can find this, then the contribution is going to be like this. Let me show you here. So it's going to be 1, 2, 3 times. Okay, I think another color is better. Okay. Yeah, it's going to be 3 times 1, 2, 3, 4, and 5. Yeah, 5 times the 4 itself. So this is the number of subarrays that include 4, and 4 is the minimum in them, times the 4 itself, the number, the minimum. So total sum is going to be plus equal to this amount. So we reduced the problem to finding a number that is the first number that is smaller than or equal when we are going to the right, and the first number that is smaller to the left. So let's see how we can solve this problem. Okay, to solve this problem, the first is smaller on the left, the first is smaller on the right, the first bigger on the left, the first bigger on the right. You should use some data structure, which is called monotonic stack. And before recording this video, I really thought, how could you solve this problem without having some prior knowledge of this monotonic stack? And I couldn't find an answer, to be honest. This is like a technique. This is like knowing to do memoization when doing DP, and coming up with this on your own. Maybe 0.1% of us can do that, but I know I'm not among them. And if you are among them, thank you for watching this video. So let's go and see what is a monotonic stack. So it's a stack that it's either increasing or decreasing. So the tone is mono, it's like 1, 2, 3, 4, 5, or like 5, 4, 2, 1, something like that. It's one of these two. In our example, it's going to be increasing. Let's go and see why. Okay, let's say we have this example. The stack, let's say, looks like this: 1, 2, 3, 4, and 5. This is the stack, and we are looking for first. I'm going to solve this one for the first number that is smaller on the left. So first I'm going to solve this, and then I'm going to solve that. So let's go and see how we can solve this part. So, and now we are looking at number 4, and number 4 in the array. And this is the stack so far. So remember, we were looking for smaller, for the first number that is smaller. So we look at the stack. Is 5 smaller than 4? No. Is 4 smaller than 4? No. So we pop it from the stack. Is 3 smaller than 4? Yes. We keep it, and let's see what happens. These are the actual numbers. So when we are writing the code, we are going to work with index, not the numbers. So just for clarity, I have worked with the actual numbers. So let's say this is the array, and this is where 3 is residing, and this is where 4 is residing. Okay, and let's say the index of 3 is 10, and the index of 4 is 15. So how many options do we have for the left side of 4? Let's count them. So it's going to be 11, it's going to be 12, it's going to be 13, and 14, and also 15. So 5 of them. So it's going to be 15 minus 10. So it's going to be 15 minus 10, which is going to be 5. And if this is empty, so for example, let's say we have a number like our stack, let's say looks like this, 4, 7, 9, and now we are looking at number 2. So this is the stack, and we are looking at number 2. So remember, again, we are looking for the first number that is smaller than 2. Okay. Is 9 smaller than 2? No. Is 7 smaller than 2? No. Is 4 smaller than 2? No. So the stack is empty. So when the stack is empty, we look at the index of 2. Let's say this is the array, and this is 2. And if the index of 2 is, let's say, 10, how many options do we have for the left side of 2? We have 0, 1, 2, all the way up to 10 itself, right? So in this case, it's going to be I plus 1, which I in this case is the index of this number. So this is the left side of each number. Let's go and see how we can solve the right side of each number. And for the right part, let's go and have another example for the right part. I have so many of these copies, yeah. Here, let's say we have the same situation here, and we have the monotonic stack, and remember, we are coming from the right, so it's 1, 2, 3, 4, and 5. And now here we are standing on number 4. So this is the stack, and the stack is coming from like right to left, and we are at number 4. And again, remember that stop before a number that is smaller than or equal to 4. Smaller than or equal to 4. So is 5 smaller than or equal to 4? No. Get rid of it. Is 4 smaller than or equal to 4? Yes. So stay there. And what happens is that if you look at the indexes, let's say this 4 is at index 10, and this other 4 is at index 15. So how many different options do we have for this, for the right side of 4? Of course, we have 10, we have 11, we have 12, 13, and again 14. So here again, the difference is going to be the number of options. So it's going to be 15 minus 10. And again, another situation, what if we have 4, 7, and 9, and now here we are looking for number 2. So this is the stack, and is this equal or smaller than 2? No. Is this equal to or smaller than 2? No. Equal or smaller than 2? No. So here we should look at the array. This is 2. and the size and the index of 2, let's say, is 10, and the size of the array, let's say size is 15. So how many options do we have for 10? We have for 2, we have 10, we have 11, we have 12, we have 13, we have 14, and that's it. So it's going to be size minus 10, which is 15 minus 10 is going to be 5. So this is the explanation. Let's go and see how we can write the code. So we need to define something const for the mod. Okay, we need some vector that keeps track of the from right side and from left side. So we need two vectors. So vector and we need to have size n and also from right. Okay. And now we need a stack. So stack of ints t. And first we do from left. So for int I equals 0, I is less than n, I plus plus. Let me bring up this. Yeah, this one. So while it's greater than or equal, so while st.size is greater than 0, while not actually st.empty, and r of st.top is greater than or equal to r of I, st.pop. And here we are going to say from left of I is going to become, so if the stack is empty, from left of I becomes I plus 1. Remember this one? I plus 1. And otherwise, from left of I becomes st.top minus I. So here, here, st.top minus I. And then we add st.push I. This is from left, and we need to do the same for from right. I'm just going to copy and paste. So before we continue, we just need to make sure that st is empty. So while not st.empty, st.pop, we just empty the stack, and then here we go from right to left. And minus 1, while ai is greater than or equal to 0, I minus minus. So while st.empty and r st.top is greater than ri, so remember here, here, stop before a number that is smaller than or equal. Smaller than or equal. That means while it is greater, we pop. And if st is empty, it's going to be n minus I. Otherwise, it's going to be st.top minus I. And then we add this index. That's it. So, and here we have int result is going to be 0 for int I 0. Result becomes result plus ri times from left of I times from right of I, and %mod. Return a result. That's it. Let's run it. Wrong answer. Output 0. So both of them are 0. Result ri from left from right. Okay, oh sorry. This should be from right. Do not copy paste. From right and from right. Okay. And wrong answer. This is good, but this one is not good. Output negative 326. This is not negative, this is positive. Okay, maybe Okay, so sorry, the problem is it's past midnight. I'm working on 10% of energy. So this should be I minus st.top. So let's see. This seems to be working. Let's have another test that is a little more complex. So 1, 2, 1, 2, a lot of ones. And a lot of big numbers, like what's the biggest number we can have? Okay, 30,000. And let's have this a few times. Okay, and see what happens. Okay, let's submit and see. Okay, integer overflow. Where could the overflow happen? Here. Okay, we can have 1 LL times this mod, and this. I think we can do this. And yeah, we need to convert it to long. Yeah, that's it. So because this was integer, it was overflowing, so I just converted to a long like this by multiplying by to a long. That's it. Let me know if you have any questions in the comments. Thank you.